recall Ito's formula. Suppose you have a stochastic differential equation. Let's say d of xt is equal to some drift term. I am taking a scalar differential equation. So d of xt dt plus some sigma txt dwt, where this is a standard Brownian motion. Recall that the meaning of stochastic differential equation, dwt as it is doesn't make sense. So meaning is stochastic integral equation. So what I mean by this is x of t will be equal to x of 0 plus integral 0 to t b of s xs ds sigma s xs dws. Remember here this is a regular integral, that means for every sample point we are just integrating. Here we are not integrating on every sample point. This is a stochastic integral in the Ito's sense. So this is a stochastic differential equation. Xt takes values in R and b and sigma are appropriate functions. This is a Brownian, standard Brownian motion, and x0 is a given random variable, x0 and this Brownian motions are independent. Now under certain conditions we know that this there is a unique solution and so on. Now suppose that f is a function. F is a function from, say we are taking time positive. So x is a function from 0 infinity cross R to R, and we want to find, and we want to find out what is the value of f of txt, f of txt. So chain rule, right? So in other words, we are interested in d of fxt. So this is chain rule. So Srikanth has already explained, so I am just recalling it. This is del f over del t, all evaluated at txt, so I am just omitting that, plus del f over del x times b txt. These are all evaluated at bxt plus half sigma square txt, all this dt, sorry, plus this is the formula. This is called Ito's formula. Now if you compare with the general, if there were no stochastic integral, then these terms are usual. Okay, this is the only term that comes, the second order term. So you need some property of f, right? We are differentiating f with respect to t, so it must be differentiable, continuously differentiable with respect to time. And here we are differentiating f with respect to x twice, so it must be twice continuously differentiable with respect to x. And again note that this is symbolic, so what it means is f txt is equal to f0 x0 plus integral 0 to t, this bracketed term ds, and then plus integral 0 to t, this bracketed term dws. So this is the meaning of, this is Ito's formula, and that plays a fundamental role in in what we are going to do today. So what we do is Black-Scholes theory. I would add the name Black-Scholes-Smeaton's theory. So what is the market? So market has only two ST. This is a stock and this is a bond. This is a bond. Now bond has a very simple evaluation. Bt equal to, B0 is 1. So B0 e to the power RT, which is e to the power RT. Therefore dBt is RBT dt. dBt over dt equal to R e to the power RT. So this is a very simple equation satisfied by the bond. It's a deterministic equation. R is the return on the bond or the rate of interest or the growth rate. Now this satisfies a geometric Brownian motion. D of ST equal to mu ST dt plus sigma ST dWt. This is called geometric Brownian motion, and Srikanth has already solved this using Ito's formula. You can solve this problem, and ST equal to S0 e to the power mu minus half sigma square t plus sigma Wt. Right? Now look at the this is just a deterministic quantity, right? And this is a constant, and you know that this is a Brownian motion. Brownian motion is normally distributed. So if you take log of this, then the log will be normally distributed. So this distribution is called log normal. This is called a log normal distribution. So these properties are well known. Log normal distribution properties are well known. In particular, you can show that, okay, easy to show that if you take expectation of ST, you can compute the expectation. Expectation of ST is equal to expectation of S0 times e to the power mu t. This is very easy to see, that expectation of ST equal to expectation of S0 times e to the power mu t. Now you compare this with Bt equal to e to the power RT, right? The bond, the growth of the bond is Bt equal to e to the power RT, and this is the expected value because ST is a stochastic process, so we can't talk about ST. Okay, so we normally, when you talk about the growth, we take the expected growth. So the expected growth, this is a given quantity, right, the initial one, and this is e to the power mu t. So mu is replacing R, right? Mu is replacing R, and hence mu is called return or interest rate or growth rate in the expectation. So it's the average growth rate. It's not since it's a stochastic process, we are not talking about growth at every sample point, but we are talking about growth in the mean. So expected growth rate or return, as they say, is mu. So that's the interpretation of this one. This can be both positive and negative, but sigma is necessarily positive, and let's see the interpretation of sigma. Now take log here. Log of ST will be S0 is usually given, so this is a deterministic quantity, plus mu minus half sigma square T plus sigma Wt, right, log of this, right. So take the variance of log of St, take the variance of log of St. Now as I said, this is a given quantity, so no variance, this is a deterministic quantity, no variance, and you know the variance of Wt is T, right. So this is sigma square times T, right. So variance relates to the second moment. So let us come to the standard deviation. So therefore standard deviation Sd of log St is equal to sigma times square root of T, right. So sigma is a very important parameter in this equation. The most important parameter is, this is the sigma, standard deviation is sigma times square root of T. Square root of T, you know, because it's associated with Brownian motion, so it evolves like square root of T, and sigma is the parameter that's always multiplying, right. So therefore the sigma, this is the most important parameter, sigma is called the volatility. It is called volatility because it represents the standard deviation. But one thing you must realize, that this standard deviation is not of St, right, but we are going for, here we are in the usual scale, while taking the return, mu is the return in the usual scale, but whereas when we are talking about the volatility, we are going into the logarithmic scale. So in the logarithmic scale, this is representing the volatility, but this is called the volatility of the stock. So these are the two very, very important parameters. Now if you look at it from a statistical point of view, standard deviation can be estimated using observed data, right, and therefore this can be estimated from the time series data, and that will be called observed volatility. We will introduce one more term called implied volatility. So this is the model of the stock, this is the model of the bond. It's a very simple model, and this is the market. Yeah, sure.
So basically you are saying that the volatility is sigma root T.
At time T.
At time T. And as the time propagates, the volatility is going to increase.
Yeah.
So when
in the logarithmic scale.
Yeah, in the logarithmic scale.
Yeah.
So when I use a particular point of time, historical volatility, to estimate the option price in the future, is not that biased priori actually?
No. This will not come. Only this parameter will come. Only this parameter will come in the option price, and T will of course come. Let's wait a little bit. Let's look at the option price formula and then see. This parameter will play a significant role. See, this is sigma is not time dependent, right? Sigma is fixed. So we call sigma the volatility. The square root of T is coming because St is driven by Wt. Wt grows like square root of T, right, in the long run, and therefore the square root of T is coming. But volatility is sigma. Sigma is called the volatility. This typically represents the fluctuations around the mean. Now let's move forward. Now what is the option? We are concentrating on European call option. So C of capital T I know is St minus K plus. This is the value of the option at the end of the day, and I want to find Ct. I want to find Ct at an earlier time. Remember, now it is the continuous time, so 0 to t. I want to find t. T may be equal to 0 also. So t, this is what is the question that I want to. Now Yesterday I did the martingale method, which I will come towards the end of this lecture. First, let's do the PDE method. Partial differential. We will derive a partial differential equation that CT will satisfy. To do that, once you look, we have an exact solution, right? ST equal to this. And therefore, if you want to calculate, for instance, S of, let's say, some future date, let's say S of capital T. How do you calculate? S of capital T, same thing you can follow. S of capital T will be some S of little t, right? E to the power mu minus half sigma square capital T minus T plus sigma right. So if ST is given, S capital T is determined like this, right? Huh? Oh, I have to write. WT minus W little t. Just this one I am elaborating. Instead of 0 I am taking any other point. So just I wanted to show you that in order to determine ST, so you need to know only S little t, right? Not the prior information. So if you want to have the value ST here, you don't need this data here, right? This data is enough, right? And that's true for every time. And this is called the Markov property. Given the past and the present, the future is conditionally independent of the past. It only depends on the present, right? So this is called the Markov property, and this will be very crucial. Markov property. In other words, the stock process is a Markov process. Okay? It's a kind of a memoryless process. Every time it builds on the present. To be more precise in mathematical terms, given the past and the present, the future is conditionally independent of the past. So, I mean, if you know from the yesterday's, okay, if there is a unique risk neutral measure, okay, then this is going to be equal to expected value of, if there is a risk neutral measure, we will investigate towards the end, okay, this will be e to the power minus r t minus t st minus k plus given ft, right? Given ft, where what is ft? Ft is equal to s of u, right? So all the information generated by the stock process up to and including time t, that is ft, right? So this is the quantity that we have to evaluate, right? But due to Markov property, this is going to be equal to expected value of e to the power minus r t minus t st minus k plus only st, it will only, right? This data, this information space starts from 0 and goes all the way till t, right? But since this guy is a Markov, this is a deterministic quantity, and this guy is a Markov process, it does not need the entire past data, it builds only on the present data, right? And therefore, this is equal to this quantity, and this tells you that this must be equal to, so this is an expectation with respect to some probability measure which you do not yet know, and we will find it out. This probability measure, it depends on obviously this little t. Capital T is given, okay, little t is the one that we are varying, we can choose little t anywhere, right? Capital T is a given quantity, t will depend on capital T, but capital T is a fixed quantity, it will depend on r also, it will depend on k also, but those are given quantities, they are not going to vary. What's going to vary is the little t and what is going to vary is therefore ST, right? ST and T are the variables. The rest are all given quantities, capital K, little r, right? These are all given quantity. So therefore CT will depend on T, right? Some function of the current time T, right? And a function of the current state S. So C will be essentially a function of the current time and the current state. Is this clear? And among other things, it will depend on all the other parameters, like it will depend on sigma, it will depend on R, it will depend on K, but those are fixed in this context. What we are varying is T, and hence we are varying ST. So by this expression, it's very clear that the option price at little t will depend on little t and the stock price, the current time and the current stock price. And this is happening because of the Markovian nature and the nature of the call. If the call price has dependent on the, for example, some, if you take some other kind of exotic options like barrier options, etc., right? So there it depends on the entire past, then this will not be true. But I am only talking about the call options where this is true, right? Now, the second thing is, now we have to, yesterday we have defined strategies, right? We have defined strategies in discrete time. We have to define strategies, right? So what will be a typically strategy? Strategy phi will be a stochastic process. Yesterday it was a stochastic sequence, right? Phi 0, phi 1, phi 2, phi 3, phi capital N, right? So it's going to be, it was a stochastic sequence, now it's going to be a stochastic process in continuous time, right? Phi t, where phi t will have two components. This will have two components, phi 0 of t and phi 1 of t, right? T lies between 0 and t. What is phi 0 of t? The holding in the bond. And what is phi 1 of t? Holding in the stock. Same, right? Now we have said that the strategy must be predictable, right? That means in discrete time, phi of n must be measurable with respect to fn minus 1. Here, how would you say that? Phi t is measurable with respect to what? Our given filtration is now ft, which is generated by st. So how would you say that in continuous time? It's a very difficult problem, right? Because what is just before t, right? So predictability, the definition of predictability is technical, okay, and therefore I will ignore that. Roughly speaking, it has to be predictable, but predictable is, in my notes it's given and you're going to upload it, right? So predictable in my notes, but at a first reading, don't worry about too much. Roughly speaking, predictable processes are those processes which are left continuous. Continuous from the left. But predictable is, left continuous processes are predictable, but predictable processes are much larger than left continuous, but don't worry about technicalities. Okay, so I'm not going to give you a precise definition of predictability. So these has to be predictable. And of course, what is the value of the portfolio? Value of the portfolio is phi 0 of t times bt plus phi 1 of t times st. This is the portfolio value, right? Just before yesterday we had k plus 1, I have now 2. K is equal to 1 here. Right? This is the value of the portfolio. Then what is the next thing we have defined in strategies? Self-financing, right? self-financing we have defined, right? So in self-financing, strategy, we have said that a strategy is self-financing only when the value of the portfolio at any time is equal to the initial endowment plus the gain. Okay, in discrete time we could write it as the inner product of phi n Sn must be equal to the inner product of phi n plus 1 Sn, but that's not possible here, right? So it has to be defined only in terms of gain. So this is the definition. Definition is Vt of phi must be equal to V0 of phi, right, plus 0 to t, the phi 0 of u dBu plus 0 to t phi 1 of u dSu, right? Why this is so? This is the initial endowment, right? And this is phi 0 u is your holding in the bond at time u, and this is the incremental change in the bond, integrate it over 0 to t. Similarly, this is your holding on the stock, and this is your incremental change in the stock over a small period of time, and therefore it is called self-financing if this equality holds. This is called GT of phi. In other words, Vt of phi must be equal to V0 of phi plus GT of phi, the gain. Remember, I have said that yesterday, the gain may be loss also, it need not be non-negative, it could be negative also. So this is it, right? This is the definition of self-financing strategy. So from this definition, we come to one thing, that this is the value of the portfolio, right? So what is the infinitesimal change in the portfolio in a small time interval? How much will the portfolio change? That will be dVt of phi, right? dVt of phi is the infinitesimal change in the portfolio in a very small interval of time. Think intuitively, right? It can be made mathematically precise. It's not incorrect, but so this is going to be equal to phi 0 of t dBt plus phi 1 of t dSt, right? Here, differentiate, right? Differentiate and use fundamental theorem of calculus. This is it, right? Now I know what is this. So this is phi 0 of t rbt dt plus phi 1 of t mu st dt plus phi 1 of t sigma st dwt, right? Now let's collate the dt terms. So this is r phi 0 of t bt plus mu phi 1 of t st, all this dt plus sigma phi 1 of t st. So dVt of phi is equal to this. Let's remember this. This will play a significant role. This will play a significant role. How to calculate the infinitesimal change in the portfolio when the strategy is self-financing. Is this part clear? Okay. Now, now the question is, I will make an assumption. It's not an assumption, it's a fact. The fact is that, so the fact is, but I'm not going to prove the fact because I will write it somewhere here. Some fact which is not easy to prove. The market is viable and complete. The market is viable and complete. It's a difficult thing to prove because it's not as simple as in discrete time. The definitions are the same, but the characterizations are incredibly complicated in continuous time. Okay, let's not get into that. Let's do the way these guys have done, Black-Scholes and Mertens. This concepts of arbitrage freeness was there, complete market is later concept. Okay, let's not worry about it, but it's a fact. Okay, at least arbitrage free. If it is arbitrage free, then we make some observation. We make some observation. This we will need, but let's make some observation. Because the market is arbitrage free, what can happen? Now, what is the aim? Aim is to price the stock, right? And how do I price it? By generating a self-financing strategy. So phi self-financing, right, such that V capital T of phi is equal to ST minus K plus, I must have, this is the call option that I am going to price, right? So I must have a self-financing strategy which replicates the call, right? And through this I am going to price it. Not using a martingale measure. I will come to martingale measure a little later, right? This is the one. Now I will write a little lemma. The proof is not difficult, but if you think intuitively, it's not necessary. Okay. Now this is also equal to CT, right? This is by definition CT, right? So since the value of the portfolio is equal to value of the option at time t, I will augment the market, and I will augment the market, and I will say that this is call option, right? Call is also bought and sold in the market, which is a fact. So my initial market was, in the initial market I had stock and bond. Now I have three instruments: the bond, stock and the call. So this is an augmented market, and the fact is that augmented market is also complete, viable and complete. Viability is the one which I am going to use. We are not going to use completeness. Okay, completeness will not be used. The augmented market is also viable in the sense this is arbitrage free. Because of the arbitrage freeness, CT is going to be equal to VT of phi. Right? This is my lemma. You want to prove it? How do you prove such a thing? I am not going to prove it. Today I am unlikely to prove anything. Huh? Because CT is also bought and sold in the market, right? If there is an inequality, strict inequality, it will lead to an arbitrage opportunity. That's the proof. If you give a mathematical proof, it will be 4 or 5 lines. But if you think intuitively, it doesn't need a proof. Because you know that this proof is complicated. This proof is complicated that the augmented market is viable. You need to prove a little bit, but if you make this assumption that the augmented market is complete, then this is trivial. There's nothing needs to be proved, right? So this is obvious, right? So this lemma is that the value of CT must be equal to the value of this, right? And we have already made an observation, i.e. CT is basically C of ST, right? C depends on the current time, C depends on the current price of the this must be equal to Vt of phi, right? So this is the lemma. Lemma ends here, that Ct of St and Vt of phi, right? So the value of the call price is equal to value of the portfolio. The reason is that that portfolio replicates the call at the end of the day, right? So therefore their infinitesimal change will also coincide, right? This implies that dCt of St is equal to dVt of phi, right? This must be, if the call price is equal to the portfolio value, their infinitesimal change in small interval of time must also be equal, right? And therefore I get something here. This is equal to right. This part is okay. This is dVt equal to dCt, right? And therefore dCt must be equal to this expression. This is where Black and Scholes were there and they got stuck. They didn't know how to proceed further, okay? But then they called their friend Martin, who was familiar with that Ito's formula. So he says, apply Ito's formula to this guy, right? Apply Ito's formula and you will be done, right? Ito's formula is, instead of C, I have F here, right? And instead of B, I have some mu S. Instead of sigma txt, I have sigma st, right? That's all. So I apply Ito's formula to here, right? So let's write down on this part of the board, right? Ito's formula, simple. So what will be Ito's formula? So here is the equation, right? And you are using Ito's formula. Ito's formula needs, as I explained, that this is Ito's formula. Ito's formula needs f must be continuously differentiable with respect to t and twice continuously differentiable with respect to x. And here the function c is unknown, right? So we do not know, we know it's a function, but what kind of a function we do not know, right? But let's make an assumption that let's apply Ito's formula assuming that it's smooth, and then we will see what happens, right? So let's write it down. Ito's formula. So if I use Ito's formula, then d of C T S T, right? This is del f over del t. That will be del C over del t, and in bracket it will be t comma st. Let's keep writing it, t comma st, right? Then del f over del s, but I will write del x, okay? With respect to derivative with respect to stock, I will denote it by x, because the typical value of st I will denote it by, instead of s I am just using the symbol x, it doesn't matter, right? So del c over, I am using del x instead of, for stock price, instead of s I am using x. Confusion? No confusion? Okay. So this is also tst. Now times what? Times what? Times b, right? What is b here? Mu st, right? b is here mu st, right? Mu st, right? Plus half times sigma square, right? What is sigma square txt? Here sigma st, right? So it will be sigma square st square, right? So sigma square st square dt, right? This is it. Then I will have a stochastic term. The stochastic term is del f over del x, so that means del c over del x I am writing tst times sigma, right? Sigma st dwt, right? This is just e to, what is x? Small x. So what I am doing is I should be writing my typical value of st is x, right? So instead of derivative with respect to s, I am denoting it by derivative with respect to x. So x is a typical value of the stock, and therefore there I was using the terminology x and here I am using the terminology s. So you can say these are s, the stock price, right? I have to differentiate with respect to the stock price, but a typical stock price I will denote it by x. It's just a symbol. If you are uncomfortable, replace x by little s. st and x. It's a symbol. Has two variable, t and st. Okay, since there is question is asked, let us call it s. Since you don't like, you are objecting, I will write s. Now you are happy?
Just explain one second. So C has two variables, right? T and let's say X. Forget the stock price for the minute. So first term you differentiate with respect to the time variable. You will get now a function, another function, which will be a function of two variables, time and the space. The time variable you are putting T, the space variable you are evaluating at capital ST. So that's what you're doing. So D2 ds square means you differentiate the second with respect to the second variable 2 times. Correct? And you evaluate, so now you get a function, right? Where will you evaluate that function? It will be evaluated at t comma st. That's all.
So x is better or s? Shall I call it x? Differentiation with respect to x. The x means the differentiation with respect to the second variable. Time del over del t means differentiation with respect to the first variable, and del over del x means the differentiation with respect to the second variable, which happens to be the stock, evaluated at tst. This is all fine. Now I have one, so let's box this also. This is an important derivation. With Merton's help, Black and Scholes could do this, and the rest they say is history, literally, because they got Nobel Prize by equating the two. Okay? Huh? No, they started a company and that collapsed. Okay, so don't use too much mathematics. Okay, get the Nobel Prize and be happy with it. So now this expression, and if you want to call it 1 and you want to call it 2, I will explain you there are a lot of lacunas in if you want to apply the theory as it is. There are many, here we are using that the rates are same, right? Borrowing, lending rates are now, this is not the valid. So there are many assumptions here which are not valid in practical life. So nevertheless, this is a very good starting point because you will get exact solution. So the DCT I have evaluated there and DCT I have evaluated here, right? So this expression is going to be equal to, from 1 and 2, this expression is going to be r phi 0 of t bt plus mu phi 1 of t st dt plus sigma phi 1 of st so I have got this equality now, right, from using 1 and 2. Now equate the dt term and equate the dwt term. You can do that. Why? The dwt term, as Srikant must have explained you, that it's basically a stochastic integral. Stochastic integral is a martingale, always a martingale by definition, and the dt integrals are, if you find it technical, never mind it, it's a process of bounded variation, okay, and if a martingale is equal to the process of bounded variation, each is equal to 0. Never mind, equate the dt term and equate the dwt term. You can do that, right? Mathematics allows you to equate the dt term and equate the dwt term. So first equate the dwt term. So this quantity must be equal to this quantity, dwt term. And from where I have written this here? This is exactly, this is the term, right? This is dct, okay? So if you equate, what do you get? If you equate, you get sigma phi 1 tst is equal to del c tst over del x sigma st, right? Sigma is positive, st is always positive, st is always positive given by an exponential, okay? So I can erase this, I can do this, I can do this, I can do this, right? Chop them off, right? So what do you get? So what is phi 1 of t? Phi 1 of t is your holding in the stock, that's given by the derivative of the option price, which is still unknown, right? But we are just writing it down. It is still unknown. And then I know that Ct equal to Vt and equal to this. So you can calculate the phi 0 of t also, right? You can equate the other part. You can equate the other part and you will get phi 0 of t, right? Ct equal to Vt, right? Ct equal to Vt. Look, Ct equal to Vt, right? This is Ct equal to Vt, right? So then C of St, this is equal to Vt of phi. This is equal to Vt of phi, but Vt of phi is phi 0 of t Vt plus phi 1 of t into St, right? But phi 1 of t has been calculated, del C over del x evaluated at Tst times St, right? So what is phi 0 of t in terms of the option? Therefore phi 0 of t C Tst minus del C over del x evaluated at Tst times St over Bt, right? Over Bt. This is all right? take this to this side and divide by Bt. Bt is a positive quantity, you can always divide, right. So if I know C, I know phi 0 t also, but the problem is I don't know C, right. I have calculated phi 1 of t as the derivative with respect to the option price, and phi 0 t, the option price minus the derivative of the option price times the stock price divided by the bond price. If I know now the option price, I know the hedging strategy. This is the hedging strategy, right. So if I know the option price, I know the hedging strategy. So far we have only equated the dw term and got this term. Now equate the dt term. We have not yet equated the dt term, right. So what is the dt term? Del C over del T. Let me, for the sake, evaluated at TST, okay, that is understood, right, plus del C over del X mu ST plus half sigma square ST square del 2 C over del X square, okay. This is equal to this guy, right. This guy is R of phi 0 of t times Bt, right. Phi 0 of t times Bt is how? C, right, minus St times del C over del X, right. Now somewhere I have missed something. No, I have made some R is missing. Oh, R is here. That's fine, right? That's fine, right? Plus I have plus mu phi 1 plus mu phi 1 is del C over del X ST, right? This is all right. Just I have equated the dt term, and now I have put the values of phi 0 t and phi 1 of t. Now look at this. Knocks off. So what you are getting? Del C over del t plus I can bring this to that side, right. So then it will be RST del C over del X plus half sigma square ST square del 2 C over del X square. Remember, these are all evaluated at TST minus R C TST is equal to 0. Have I done this? This is Black-Scholes PDE. Now let me write it in the way PDEs are written. Okay. Now stock price will be observed at time t, right? So suppose ST equal to X. Suppose ST equal to X, then write down this equation. It will be del C Tx over del T plus Rx del C Tx over del X plus half sigma square X square del 2 C over del X square Tx minus R C Tx is equal to 0. Right? I have observed the stock price ST equal to X. If the stock price observed is S2 equal to X, what is the PDE? PDE is this, right? Just I have written this, del T over del T, Tx, right? R, ST is X, so Rx, del C over del X plus half sigma square X square, del C over del X square minus RC equal to 0, right? And what is C of capital Tx? C of capital Tx is X minus K plus, right? So this is a PDE. This is called Black-Scholes PDE, very celebrated Black-Scholes PDE. So Black-Scholes not only derived this PDE, they solved it exactly. So where is the PDE formulated? If you are a PDE guy, where is the PDE formulated? PDE is formulated, the time horizon is 0 to t, right? The end time you know in terms of it is between 0 to t, right? And where is x lies? X lies between 0 to infinity. So in other words, if this is your time axis, so this is 0 to t. No, if your x axis, so it's the x must be positive, right? So it's the upper half plane. It's the upper half plane. Now, in my notes, the details are given, but let me write down the solution, because that will take time. The derivation is, let me write down the solution. This PDE can be solved exactly, and that is the power of Black-Scholes theory. You can solve this PDE exactly, and the solution is given by Ct of x. This PDE can be solved exactly. By a proper transformation, this PDE can be converted into an heat equation, and heat equation can be solved exactly. So the exact solution as derived by Black-Scholes is given by x phi, I will explain everything, x phi d plus x t minus t minus k e to the power minus r t minus t phi d minus x t minus t, where d plus minus x t is equal to log x over k plus r plus minus half sigma square t over sigma square root of t. This is, let me write one more line and then, and phi 1 of t, which is denoted phi 1 of t, which is denoted by delta t, is equal to del c over del x, and this happens to be equal to phi of d plus x t minus t. What is an phi x? Now let's analyze this. Let's analyze this. So this is a PDE that can be solved exactly. Black and Scholes did it. and the derivation is given. It's just, making some transformation here and there, logarithmic transformation and just routine calculations, you can solve it. So what is phi x? Phi x is the so-called error function, right? Right? It's the cumulative distribution function of the standard normal random variable. These are tables are available, right? So the option price is in terms of the normal distribution, the x is the stock price times phi of some function minus k e to the power minus rt minus t, phi of some other function, where what is the other functions? D plus minus, that is d plus and d minus, x of t is log of xk, k is the strike price, plus r is the interest rate, plus minus half sigma square, sigma is the volatility, times, so here it will be t minus t, so here it is t, and what is your hedging strategy? The del c over del x, as we have observed, and you can calculate that to be equal to phi exact. So Black-Scholes formula, if you know the formula, if you know the parameters, and you want to find the price of a call, you don't need a computer, a scientific calculator is enough. Those days in 70s, when this was done, people used to calculate Black-Scholes option pricing and check, because the calls are also bought and sold in the market, they could easily check this, right? So this is called the delta hedging. Okay, this is called the delta hedging, and delta is also exact. Now if you notice this, there is no mu, right? And if you notice my previous one, the binomial one, whose limit is this one, right? In the binomial we started with a parameter p0, right? Right? And when we wrote the formula, I forgot to mention it yesterday, but remember in the last formula was depending only on little p, and little p was b minus r over b minus a. P naught was nowhere there, right? So in binomial model also, that initial p naught does not play any role. Here also mu is not playing any role. In other words, if I know the stock price, then the option price has no dependence on the growth rate of the stock. That's the formula, right? And here is your hedging strategy. Everything is explicit, and though there are some assumptions which are not true in practice, on the other hand, if you make the realistic assumptions, you won't get any formula. So this will gives you some, hand-on what the option price could be. So any question? You can draw the picture. You can draw the picture, and so let me, if you want to draw the picture, you need a little more. This is called delta. This is called delta, and I will write two more Greeks. This is how the option price, this is the hedging, this is also the hedging strategy, and also the sensitivity of the option price with respect to the stock price, right? Del C over del X. So this is the sensitivity. I mean, how the delta gives you an idea of how the option price is changing with respect to stock price. There are other two, and those expressions are also very, very explicit. The other two expressions are important is theta, capital theta, which is also a function of time. This is del C Tx over, so given the fixed stock price, how is it moving with respect to time? This is called theta, and this is minus Rk. You can calculate this. This is a matter of calculation because everything is now explicit. Phi d minus xt minus t minus sigma x 2 square root of t minus t phi prime, the derivative of d plus xt minus t. One more and then I will explain. Gamma equal to gamma t equal to, this is the second derivative of, for a fixed t, this is the second derivative with respect to the stock price, and this is equal to, if you calculate, this will come out to be 1 over sigma x square root of t minus t phi prime d plus xt minus t. Now you wanted, so what are the implications of this? This is the sensitivity analysis. This is the sensitivity with respect to the stock price and also gives the hedging strategy. This is sensitivity with respect to time, that if the stock price is fixed and if you make a small time change, the theta is negative, right? Theta is negative, right? All these quantities are positive, right? So theta is negative. And how about gamma? No, gamma is, this is positive, right? This is a density, right? Phi is a cumulative distribution function. So phi prime is a density, so positive. So gamma is positive. Gamma is positive means for a fixed time, the second derivative is positive. If the second derivative is positive, how does the graph look like? Convex, right? It's convex. So you wanted a graph, right? The graph would be like this. Typically the graph would be, as x increases for a fixed t. So you can't draw the graph of CTX, right? There are two variables. If you fix time t and you want to draw a graph, the graph will typically look like this. It's a convex because gamma is positive. Now using these sensitivity, you can do a lot of analysis, but I really don't have time. During the discussion, I can come to it. I want to spend the remaining 35 minutes in risk neutral pricing, because that's how risk neutral price, see, this is in a way lucky situation that you get a PD. You may not be lucky all the time if the model is slightly different, right? This is the simplest model. So this calculation is a very clever calculation, but it doesn't work all the time. A more powerful approach, it came later.
If you want to test this model, imagine it's working or not in real world. Imagine I take option prices from this any exchange. There's no way that I can fix time and change the stock prices.
No, but option prices are also available, right? So you can test.
There's no way I can fix time and change the stock prices.
No, you cannot. But you have observed the stock price. You have observed the option price. Okay, and then you have already the parameters are you are known, so you can check the model.
Whether that particular derivative is working or not, I don't know.
Which derivative? This one? No, these are for sensitivity.
But how to test this actually? There is no way I can fix the time and have the stock price. Model is correct. Believe your model. Then it will tell you how is the price.
Now, quickly we will have a discussion session today, right? So let me now quickly come to what is called risk neutral measure, risk neutral valuation. We will have a detailed discussion in the afternoon after Srikant's talks. Risk neutral valuation. So to do that, I will, Girsanov's theorem, have you stated? No, okay. So a very simpler form of Girsanov's theorem, which is not Girsanov, but basically a Cameron's theorem. Okay. So suppose WT, standard Brownian motion on omega Fp. This is a standard Brownian motion, right? Now suppose Q is some real number, then you perturb this by Qt. This is no more a Brownian motion, right? Because you have perturbed it by some Qt, right? So this is not a BM with respect to P, right? It's not a Brownian motion with respect to P. The question is, can you now change the P so that it becomes a Brownian motion? And the answer is yes. Okay. So here is the theorem. You define the stochastic process, set mt is equal to exponential minus qwt minus half q square t. T lies between 0 and say less some capital T. Then this is exponential martingale, Srikant. Exponential martingale you have seen, right? So this is an exponential martingale because this part, and I have just subtracted its quadratic variation. So you can prove that this is a martingale. You can prove that MT is a martingale. And defining that, using this, you can define a probability measure P tilde A is equal to A MT dP. Then the conclusion is A. So let's call this as WT tilde equal to, right? Then WT tilde is a P tilde Brownian motion. P tilde Brownian motion. With respect to P, it's not a Brownian motion, but with respect to the new one, it's a Brownian motion, and the relationship between dP and dP is equal to MT. This is called, if you know math, if you know little bit of probability theory, this is called the Radon-Nikodym theorem. This is called this is Radon-Nikodym derivative. This is called Cameron's theorem. I will use this little part. If you are wondering why this is happening, suppose X is a random variable, right? Which is standard Gaussian, right? Standard Gaussian, that is N01. Then X plus mu is not a standard Gaussian, it's a Gaussian, but not a standard Gaussian. But you want to make it a standard Gaussian, right? So you will change the measure. You will change the measure using obviously some exponential quantity, right? So same thing we are doing for a stochastic process. WT is a Brownian motion with respect to the measure P, but I am perturbing WT by some QT. So this is not a Brownian motion with respect to the original measure. Then you have some exponential quantity MT, which is an exponential martingale, and then you define a new measure. This will define a new measure because MT is a martingale, consistently define a measure, and you can show that this wiggle WT tilde is a P tilde Brownian motion, and the relationship between dP and dP tilde, that the derivative of P tilde with respect to P is this MT. This is called Cameron's theorem.
Q is not a variable.
No, Q, no. Q is real drift, precisely. This is a Brownian motion with a drift. Okay, if q is positive, positive drift, q is negative, negative drift. But I have changed the measure in which it's a standard Brownian motion. Drift is absorbed in this martingale. In other words, drift is absorbed in p tilde. Now I will use this theorem very quickly. So let's see the market model. The market model is here. This is dBt is r and dst is this, and I have already said E of st is E of s0 times e to the power mu t, right? So in other words, the stock grows at mu, right? And the bond grows at r, typically, yeah? No, Brownian, no, you have been given a Brownian motion, you are perturbing it. Okay, so application will answer your question. I'm just coming. Why I need this will be absolutely clear. Now, you look at the bond is growing at the rate r, right? The stock is going at the rate mu. So, typically which will be larger? Mu will be typically larger, right? Otherwise, why should you invest in a bond, right? Typically mu will be larger, right? And therefore, stock is growing at a larger, and therefore with respect to we have a probability measure, we have a probability space, okay, in which the growth of ST is typically higher than the growth of the bond. As I said, we want to have an ideal world where everything grows at the same rate. Is it possible to create an ideal world, right? Yesterday I told you how to create an ideal world and gave the details, and from binomial model I showed you that the ideal world is unique. There is only one ideal world. Now let's see, here also the ideal world will be unique. How to do that? So it's very easy, that replace this mu by r and then you will be ideal world. Okay, so I will do this as by force I will do r st dt, right? Since I have added, I have to subtract. So I have to, so this will be mu minus r st dt plus sigma st dwt, right? So I will call this as r st dt plus mu minus r over sigma This is correct? Sigma will be outside. This is correct now, right? I call this guy as dwt wiggle, right? So what is dwt wiggle? So this is equal to r st dt plus sigma st dwt tilde, right? Now what is my dwt tilde? What is my dwt tilde? Dwt tilde is mu minus r over sigma dt plus dwt. In other words, what is my wt wiggle? This is mu minus r over sigma t plus wt, right? Is that okay? This is okay. Now, is Wt tilde a Brownian motion with respect to the original probability? Everything has been posed on a given probability space, right? This is the market probability space. Is Wt tilde a Brownian motion? The answer is no. But if it were a Brownian motion, if Wt tilde were a Brownian motion, what will be the growth rate of St? R, right? If Wt tilde, if I can make Wt tilde a Brownian motion by changing the probability measure, by changing the realistic world to an idealistic world, what will be the growth rate of St in that world? R, right? I have matched it. So all I need to do is find a suitable probability measure with respect to which Wt tilde is a Brownian motion, and the answer is given in my theorem, right? What is Q here? What is Q here? Mu minus R over sigma. What is mu? Return from the stock. What is R? Return from the bond. So what is mu minus R? It is the excess return on the stock divided by the volatility. This is called the risk premium, the market price of risk, or this was introduced in CAPM by Sharpe, right? So this is also called Sharpe index, right? This is risk premium. There are many names. Risk premium or market price of risk. Risk in CAPM, this is called Sharpe's index. This comes in various ways. Mu minus R over sigma, the excess return per unit volatility. It's a very, very important thing. Now you know what is P tilde. P tilde has to be, so what has to be P tilde from that theorem? Right? I have to define dp tilde over dp, dp tilde over dp equal to m of t, right? What is m of t? Is e to the power minus q. So minus q is mu minus R over sigma t minus half q square mu minus R over sigma square times t, right? This is m of capital T, right? This is m of little t, right? M. Where? Oh, yeah. This is Wt, right? Oh, yeah. This has to be the quadratic variation of this. Sorry, thanks. Right? So if I do this, then dst equal to r st dt plus sigma st dwt, right? This is a GBM, right? Geometric Brownian motion, right? So I know the solution, right? The solution is, now we are looking through a different angle. Now we have changed the world, changed the probability space. Now my probability space is omega fp, and this is the only risk neutral measure. Okay, why it is a risk neutral measure? We have to prove that this is a martingale measure, right? So what is st tilde here? The discounted stock price. The discounted stock price is e to the power minus RT times ST, right? So let's see if this is a martingale. So what is dst tilde? Right? dst tilde is d of e to the power minus RT ST. Is that okay? So this is the chain rule. This is st times d of e to the power minus rt plus e to the power minus rt times dst, right? Chain rule. So this is minus r e to the power minus rt times st dt, right? And this is e to the power minus rt r st dt plus sigma st dwt tilde. Gets cancelled, right? So what is the answer? The answer is so continuing from there, ds tilde equal to, what am I left with? I am left with is e to the power minus rt sigma st, right? In other words, right? So this is just a stochastic integral plus some given quantity. Okay, a stochastic integral is always a martingale. By definition, the stochastic integral is a martingale, and therefore the discounted stock price is a martingale, and therefore p tilde that we have considered is a risk neutral measure, and we have calculated the risk neutral measure because by matching the growth rate, we have matched the growth rate. So it has to be a risk neutral measure because we have created a Brownian motion which matches the growth rate, and therefore, and one can prove, this proof is not simple, that this is a risk neutral measure, and one can prove that this is the only risk neutral measure. There is no second risk neutral measure. Therefore the market is the second fundamental theorem, first fundamental theorem, I am not giving it, they are very, very complicated, but nevertheless, then what will be the option price? What will be the option price? Tell me now. What will be CT? I wrote this beginning, right? CT will be expectation with respect to the new probability measure. P tilde, I will calling it E tilde of e to the power minus r t minus t st minus k plus given ft, right? But given ft, as I said, by Markov property, it must be given st, right? Now I can calculate this. How do I calculate this? Let's see. I will calculate this. This is e to the power minus r t minus t is a deterministic quantity, right? It doesn't appear. E tilde, and I want to calculate, then I want to calculate Ct of x, right? That means st equal to x, right? So this E of st, what is st? St equal to st e to the power r minus half sigma square t minus t plus sigma wt minus wiggle, right? Wiggled, right? I can solve this equation explicitly, right? This is a geometric Brownian motion. right? Geometric Brownian motion can be explicitly solved, right? D of st will be s of 0 e to the power r minus sigma square. Mu will be replaced by r, that's all, and w will be replaced by w tilde, right? So this is the, so s of capital T is st times e to the power r minus half sigma square capital T minus T plus sigma, that guy has the same as Wt tilde minus Wt tilde minus k plus, given st equal to, I am assuming that the stock price is x, right? Given st equal to x. So this is no more a random variable because st is equal to x. So this is a given number, and what is that given number? This is equal to e to the power minus r t minus t, expectation of st is x e to the power r minus half sigma square t minus t plus sigma Wt tilde wiggle minus Wt wiggle minus k plus, right? Now there is a challenge, okay? This is a constant, right? In the expectation, I am looking at the random variable. This is the expectation of a random variable. I want to know what is the, if I know the distribution of a random variable, then I can always, so what is the expectation of g of x? Expectation of g of x is integral gx of, right? If you know the density, f of xx dx, right? This formula we all know. Expected value of gx is integral of gx with respect to the density of x. Now can I calculate the density of these guys? If I calculate the density, then I am done. This has nothing to do, it creates no problem. This guy creates no problem, it's a constant. And what is the distribution of Wt tilde Wt? What is the distribution of this? This is normal, 0, right? So this is the normal distribution. So e to the power, that will have log normal distribution. You can compute its density, and then once you compute its density, you can compute the integral. Just an expectation of a random variable, right? A function of a random variable with respect to the log normal distribution, and you can compute that, and you will get exactly this without getting into PDE. PDE is not necessary. Without getting into PDE, you can do that. And I leave it as an exercise. This exercise is routine exercise, because after all, what are you doing? You are doing, you have to calculate this, right? Gx is, what is Gx? Gx is just this is Gx, right? And you know the density. So you just have to evaluate, but evaluation will take at least 3 pages. 3 pages of a routine but tedious exercise. Tedious, but so go do this challenge. Evaluate this integral. Okay, just a very, very routine exercise in probability. Evaluate and check that you are getting the Black-Scholes formula without anything. Now the advantage of the risk neutral is that this is the simplest, and you know the simple model is not really true. Okay, the R is never fixed, you know, mu is changing, sigma is changing, and all that. In all that scenario, this simple thing will not work. But nevertheless, such a formula such a formula is always valid with respect to some measure. If you can compute the risk neutral measure, then you can use Monte Carlo to evaluate the option price. It is not giving you a hedging strategy, it is only giving you an option price, remember. But we have got the hedging strategy, right? If you do some numerical computations, hedging is practically impractical. You can't really hedge it. Nobody hedges in reality. So forget about hedging, compute the price and be happy with it. The theory gives you a hedging, but the hedging is, if you really calculate, if you want to sell a call, do some exercises from Hull, if you want to sell a call, you have to borrow a huge amount of money from the bank to hedge that call, which is very unrealistic.
This kind of idea of the curvature that we have there, certain stock prices, that curvature arises in the bond pricing also.
Bond, if you, I mean the defaultable bond, right? Yeah, defaultable bond will have a similar one.
So the curvature here is important to estimate the exposure of risk actually.
Yeah. So
suppose we are valuing the price correctly, but the curvature is not right. So the exposure to the option is something which we don't know actually. That's what I mean to say. So suppose the Black-Scholes formula at a point of time is right for the valuation of option and we get the right value. But the curvature is not right. So if the curvature is not right, basically the risk exposure of option is something that we don't know.
No, but I don't have time now. Using, you can use the delta hedging and long gamma. So in a short period of time, if you use a strategy called delta hedging and long gamma, in either way you will not lose. If you read Schraeb's second book, and in my notes also given, okay, there is something called long gamma and delta hedging. Using a delta hedging and long gamma simultaneously, okay, you will not be a loser. You can protect yourself using such a strategy. Long gamma and delta neutral, long gamma. You can do that, but it will take time to explain. If you look at my notes, the question that you are asking is probably there in my notes on page 20-21. It's given there how to protect yourself against sudden changes in the stock price, right? Yeah, you can protect yourself using an appropriate portfolio. That portfolio is given here. Now there are many generalizations possible, right? What are the generalization possible? You can have mu dependent on time t. You can have sigma dependent on time t. Then there will be no problem. So you have calculated an option price, right? Here the option price is remember the option price. If you look at the option price depends on the current time t, right? It depends on the terminal time, capital T. It depends on the strike price, right? It depends on the volatility, and it depends on the stock price, of course. So these are the 1, 2, 3, 4, 5. That's all, right? Now suppose mu is a function of time and sigma is a function of time. Mu anyway doesn't matter. Mu is not coming, so you don't have to worry about mu, right? So you have to worry about sigma. So if sigma is a function of time, then what you do is you calculate a sigma bar, which is 1 over t 0 to t sigma square t dt, and take this and replace sigma into sigma bar. So this is the average volatility, right? So if sigma is a function of time, again Black-Scholes formula is valid, the market is complete, everything is fine, and replace sigma by the average volatility. It will work. The second layer of difficulty is, suppose any, as long as it is deterministic. As long as it is deterministic. Suppose I have written sigma t, right? Not sigma t, anything. This is a deterministic function, it will work. Deterministic function will not violently fluctuate. Okay, so this is fine. Now you can go one more step further. You can say that my return is also stochastic. My volatility is also stochastic. Now whenever we stochastic, you have to, it depends on which filtration, right? If it is a stochastic process, okay, how do you know that stochastic process? By which observation, by which information space? If the information space is the same as the stock price, that means if you observe the stock price, you can observe the stochastic volatility also. Then again the same thing will be, same formula will be valid, except that you have to find expectation here. This will be sigma omega and there will be an expectation here. Again, in other words, the market is arbitrage free and complete. But suppose you have a volatility, mu is not important, you have a volatility which is stochastic and which is extraneous stochastic, that means that's not adapted to the stock process, but there is a second source of noise. One source of noise is this, and the volatility is also stochastic, but coming from a second source of noise, right? So you have two independent sources of noise and you have only one stock price which you can buy and sell to hedge yourself. So if you have a lesser number of instruments to buy and sell than the number of noises, typically the market will be incomplete. If the market is incomplete, which is the realistic place, then the option price is not unique. Not every contingent claim is attainable, and then the theory is very rich but nevertheless technical. This is the starting point of option price. There are what is called stochastic volatility model. Now, there are various stochastic volatility model, Heston's model, all those things. What I am trying to say is that this is just the beginning. If you learn this, you can proceed further if you are interested. They will be also, if you change any of these assumptions, different lending rate and different this, then the market will be incomplete. Again, there will be lot of issues. So issues are resolved. Here, how are we resolving the issues? By replicating, right? By a replicating strategy. There you have to use a super replicating strategy. That is, your VT of phi is greater than or equal to the contingent claim. V capital T of phi is greater than or equal to the contingent claim. So take all the super replicating strategies and take the infimum of that. The other player can do a similar thing. He takes a sub-replicating strategy and take the supremum of that. That will give you a lower bound and an upper bound of the option price. Any price between the lower bound and upper bound is an arbitrage free price. It is arbitrage free, not including. The open interval between L is the lower bound, U is the upper bound. The open interval between L and U, any price is an arbitrage free price, and there are uncountably many. Now is the gain. Now is the game, between buyer and seller. The buyer will try to sell it at a higher end, the seller at a lower end, and seller is anyway taking a risk. So he will try to minimize his risk but maximize his profit. Here it is the other way, and it becomes very, very interesting. In such a scenario, you won't always get these kind of equations. Okay, in discrete time they are solved by linear programming methods, okay, with inequalities and so on, in continuous time, they are the so-called variational inequalities. This is an involved thing, but the real challenge lies when the market is incomplete. Complete market, everything is fine. Okay, thank you very much.